In this video, I'm going to go over a few things that you need to solve projectile motion type problems. So if we remember back to one-dimensional kinematics, there was a whole bunch of things about scalars and vectors. What are they? We defined displacement, velocity, acceleration, all this stuff, and I'm just going to go over that again, and plus some extra, minor details. So let's get right into it. So I just want to let you know in this video, we're not going to be doing any examples. We're just going to go over some stuff, and then the next couple videos, I'm going to go over what happens. I'm going to go over some of the famous problems in projectile motion, like throwing a ball off a cliff, or a cannon being shot, or a cannonball being shot out of a cannon at some angle. And I'm going to teach you how to find all the speeds of the problem, but also what is the speed right before it hits the ground? What is the range? What is the height? And how do you find the angle that cannonball is released from? So let's just get right into the basic stuff. So first thing you want to know is that d equals to vt, and the distance only equals to the velocity times the time when we have constant speed. Okay? And in these type of problems, we have constant acceleration. So I'm just going to write that down. I'm going to get rid of this, and I want a blank page, and I just want to document here all of the constant acceleration equations. So when we have, when we have constant acceleration, you're going to use one of these, I think there's five equations. So first of all, VF, and what do I mean by VF? I mean the final velocity is equal to the V0, the initial velocity, plus the acceleration times the time. Now that's number one. Number two, final velocity squared is equal to V0 squared plus 2 times the acceleration times the displacement. Next, displacement or distance, right? This could be distance too, I'll explain them after. Let's just go over the equations. So d is equal to 1/2 of v0 plus v final. Now, if you add two things together and divide it by 2, that's the average, right? So this is the average velocity, and this is also multiplied by time. So actually this equation is v average times time. Next we have d is equal to initial velocity times time plus 1/2 acceleration times squared. I almost forgot that one. And of course we have, I'm going to add this one, d is equal to velocity times time. Okay. So here are the acceleration equations, and as you can see, we have final velocities, initial velocities, acceleration, time, and displacement, distance, whatever, right? So let's go over what's in and what isn't in some of these equations. So in equation 1 here, we can see that it doesn't have displacement. So if you're given a problem and it says to find the displacement, you can't use that equation. And what if you're given a problem with displacement? Do you really care about that equation? So this is a good thing to know. So you probably want to memorize what these, what they don't have. So then you can, just mindlessly know which equation to use. You don't have to use all your energy thinking about it. So I'm going to put in blue what they don't have. So x, we have no displacement. Next equation, what doesn't it have? Okay, it has final velocity. Okay, it has initial. has acceleration, has displacement. Oh, we're missing time here. Okay, this equation doesn't have time. So if we're given time, do we really care about that equation? No. Oh, next one. The next one doesn't have acceleration. So we have displacement, velocities, time. Don't have acceleration in that one. Okay, so that's good. Next one. We are given displacement, initial velocity, time, acceleration, time again. Oh, final velocity is missing in this equation. Okay, and the next thing I want to talk about is the difference between speed and velocity, difference between displacement and distance. So let's get a new page here. Now, before we go into that, we have to remember what the difference between a scalar and a vector quantity is, right? So I'm going to do scalar on this side and a vector on this side. Okay, scalar, vector. Okay, well, let's say I took 10 paces. I know it, we'll say steps. I took 10 steps to the other side of the room in a straight line. Okay, and I don't tell you directions. I just told you I took 10 steps to the other side of the room. No directions are needed. That is a scalar quantity. Now, if I told you I took 10 steps and then to the right, and then I took 10 steps to the left, and then I went backwards a few steps, and then I finally got to the other side of the room by taking 3 steps straight, that's a vector quantity. There's a ton of information in there. There's direction and magnitude. We want to know how many steps I took and how I got there. With a scalar, we don't care how you got there. We just want to know that you got there. We want the magnitude, right? So let's remember that. I'm going to write that in blue. So scalar, magnitude. And by magnitude, I just mean like the value that comes out of it. So if I say the speed is equal to 15 meters per second, that's its magnitude. And by vector, I mean a vector is magnitude and direction, so plus direction. And if I say the velocity is equal to 15 meters per second north, now we're given a magnitude and a direction, so it's a vector. And we denote vectors with little arrows on top of them. And scalars, they don't have anything. So does that give you a little bit of a hint between the speed and velocity? So let's say we had a car, and I told you the car went up to 60 miles per hour. It's a pretty slow car, but that was its max it can get up to, 60 miles per hour. Would you call that velocity? No, right? You would call that the car's speed. Now, what if I said the car went 60 miles per hour to the left, and then it took a turn to the right, and then went at 30 miles per hour and returned back home? Do we care about direction? We definitely do. Do we care about its speed as well, its magnitude? We definitely do. Now we call it velocity. Okay, so that's the difference between speed and velocity. So speed is a scalar. So speed is a scalar, and then velocity is a vector. So now the difference between distance and displacement. Well, you can probably infer that distance is a scalar quantity, and we denote that with d, and that displacement is a vector quantity. So we're going to put a little arrow up there. So I wanted to provide a visual example of, how displacement works, because I said earlier, taking steps to the other side of the room, right? And we said that if we care about directions when taking these steps, then we would call it displacement. But if we didn't care about direction, then we got to the other side of the room and we called it a distance, right? So here's how that works. I think this is a good example here. So let's say we have a number line. And in this number line, we have numbers from 0 to 4 in both directions. Okay, so we go into the negative here. And the negative, why are my numbers looking like that? The negative direction is to the left. So I'm going to call this the left side. And this is called the right side. And we are a little, pretend we're a car. And you ask me for how to get to the right side. And I'm in the center here. And I'm not really sure where to go. Sorry, you're not really sure where to go. And I tell you, so you're going to go 4 miles. And you say, okay, I'll go 4 miles. And this is a very simple world. So you have 2 choices. You go left or you go right to get these 4 miles. All right, so I'm going to go 4 miles. Did I make it to 4 miles? I did. And I made it to the right side. Great. What if I did this? Did I make it to 4 miles? I did. So the distance here is 4 miles. And the distance here is also 4 miles. You see how we didn't specify a direction when giving information. I just said go 4 miles. Well, that's distance then, right? And you might be saying, well, no, this is negative 4 miles. How could something be negative 4 miles? How could you have a negative distance, right? Distance is always positive, but the negative tells you what direction it goes in, right? So when you start these problems, you're going to usually, state your positives and negatives. You're going to draw something like this, little mini axis that you put in the top, left, or right of the page, and you're going to say positive. So that tells me that the the x-axis on the right side is positive, and if you go upwards on the y-axis, that's also positive. So since we're going left on our number line here, we would indicate that with a negative symbol, but we still go 4 miles. The distance, the value for the distance doesn't change. What if I told you the direction now? I said, okay, you're going to go 4 miles, but to the right side. And we travel 4 miles right. Well, then we would say the displacement is 4 miles right, or we would denote that as just positive 4. And we understand that it goes right because of our coordinate system that we defined, right, up here, because positive means right. Now, what if I said go 4 miles to the left? Now our displacement would equal to either 4 miles to the left, or it would equal to negative 4 miles. And we don't need to specify direction because we did by putting this negative sign here because of our coordinate system. Our coordinate system says this side is negative. Well, I should say down here because the negative y-axis there, right? And that's how that works. But that still really doesn't explain displacement. So we know that distance is the ending point minus the starting point, right? Well, displacement is the same. We have an end point minus a starting point. But the thing is, displacement could be in more than one direction. If I now live in a Cartesian world here on the x and y axis, and I displace myself all over the map here, I'm going up, I'm going right, I'm going up again, Well, now there's more than one component to our displacement. It's not just d2 minus d1. Now our total displacement is the displacement in the x direction plus the displacement in the y direction, depending on the signs, right? Like that might be down, that might be up, that might be to the left, to the right, and that changes the sign we put here, because if our displacement in the y direction is downwards, then, right, like, we remember this by making a coordinate system, right? And that's very helpful for the person marking you, and it's very helpful for you as well, just so you don't mess up positives and negatives. So we would have, dx being displacement in the x direction. That would be dx1 or dx2 minus dx1. And then we would have dy. That would equal to dy2 minus dy1. And our total displacement, let's say, if our total displacement was 0 in the y direction, it would equal only displacement in the x direction, right? And if it was 0 in the x direction, it would be only equal to the displacement in the y direction. But what if our displacement represented a right-angled triangle? Then what? Then we would use Pythagorean theorem, right? dt is equal to the square root of dx squared plus dy squared. And that's all you really need to know about displacement until we get into some example problems. A few other things that are probably useful. Velocity is the displacement over time. The acceleration is the velocity over time, right? Speed, you could probably guess what speed is, the distance over time. Now, is there anything else we need to know? The average. Now, V average, remember, the average of anything is, two things, and then divided by 2, right? So we have, in this case, we have the initial velocity plus the final velocity divided by 2. And if we wanted to take the averages of a distance or a displacement, of course it's the same thing, right? We have some, distance that we start at, and then we have some distance that we end at, and then divide by 2. That's the average of those distances. And that's pretty much all you want to know about projectile motion stuff at the beginning. But the thing is with projectile motion that's different from one-dimensional physics is that it's in 2D. And if you want to learn about components, you should watch my trigonometry video. But I'm going to give a little bit of an explanation of something. So let's say we had a velocity. I'm going to use a different color here. If there was a velocity vector here, I just gave you some random velocity vector. Let's say I shot a cannonball at some angle. Well, this velocity vector is pointed in which direction? Please don't say diagonal. Earlier, when we were using the number line, we only could go left or right. But since this velocity vector is diagonal, we have x components and y components to our direction. So I went some distance in the x direction. Okay, we can stop now. We ended here, right? But I also went some height in the y direction. And that means our velocity has a component to it in the x direction and a component in the y direction. And we can actually calculate these components using trigonometry. So what if I wanted to find the x component of velocity? Remember how velocity like, was v2 minus v1, right? Well, what if I wanted to only find it in the x? You wouldn't start putting in the final and initial destination, the final destination from the y, right? You would only use the x, so like somewhere along the x-axis. So it would be vx, v2x minus v1x, right? Same with y, v2y minus v1y. And what if you wanted to find the total velocity? Well, we use special triangles, right? We use a right angle triangle. We do trigonometry, we get some angles, and we also can use Pythagorean theorem, right? If we remember, c squared is equal to a squared plus b squared. So if we substitute, you know, the v in there for the c, and then the vx and the vy for a and b, we solve for c here, and we find that vx squared plus vy squared is equal to our velocity, our total velocity. And if we want to figure out what angle that velocity is at, because of course we need a direction, so we need an angle, that's going to be the inverse tan of the y component of velocity divided by the x component of velocity. And that's all I want to cover in this introduction video. In the next video, I'm going to cover dropping a ball off a building or throwing a ball off a building. And then the video after that, cannonball. So I hope you enjoyed this video. Watch another one. Subscribe to my channel if you like this video. If you hate it, don't. And give me a constructive comment. Thank you for your time and enjoy the rest of your day.